In this presentation, we're talking about, no.
Okay, it's recording. Hi, this is Michael.
And I'm Jason.
And in this project, we decided to do breadth first search for our choice of algorithm. So then you're probably asking, what is breadth first search? Breadth first search, or also called as BFS, the algorithm is used to search a tree or graph data structure for a node that meets a set of criteria. It begins at the root of the tree or graph and investigates all the nodes at the current depth level before moving on to the next nodes and to the next level. You can solve many problems in graph theory via breadth first search. For example, finding the shortest path between two vertices from A to B is determined by the number of edges. In a float network, the Fulkerson method is used to calculate the maximum flow, and when a binary tree is serialized, deserialized instead of serialized in sorted order, the tree can be reconstructed quickly. Now, what's our motivation? So there are several reasons why you should use the BFS algorithm to traverse graph data structure. The following are some of the reasons, the essential features that make BFS algorithm necessary and kind of distinct from other types of algorithms that are similar. So the BFS algorithm has a simple and yet reliable architecture. The BFS algorithm also helps evaluate nodes in a graph and determines the shortest path to traverse nodes, like we said before. The BFS algorithm can traverse a graph in the fewest numbers of iterations possible. The iterations in the BFS algorithm are smooth, and there's no way for this method to get stuck in an infinite loop. And in comparison to other algorithms, the breadth first search algorithm has a high level of accuracy. Now, Jason will explain our application of the algorithm.
All right. So for this for application of breadth first search, most of the concepts in computer science and real world can be visualized and represented in terms of graph data structure. BFS, or breadth first search, also short for BFS, is one such useful algorithm for solving these problems easily. The architecture of BFS is simple, accurate, and robust. It is very seamless. As it is guaranteed that the algorithm won't get caught in an infinite loop. So these are just some listings that we have, some applications that we have in real world, such as like shortest path and an unweighted graph. The short path is the path with least number of edges, like our GPS, like what we use in our phones or whatever to navigate through traffic. GPS navigation system, breadth first search is used to find the neighboring locations from a given source location. And we have finding path. We can use BFS to find whether a path exists between two nodes. Finding nodes within a connected component. Breadth first search can be used to find all nodes reachable from a given node. Social networking websites as well. We can find number of people within a given distance K from a person using breadth first search. P2P networks and P2P peer-to-peer networks like BitTorrent. BFS is used to find all neighboring nodes from a given node. Search engine crawlers, the main idea behind crawlers is to start from source page and follow all links from the source to other pages and keep repeating the same. DFS can also be used here, but breadth first search, or I don't know why. Anyways, BFS has the advantage in limiting the depth or levels traversed. Later in the presentation, we also give a few details of DFS because we mentioned it in our report, in our experiment that we did. So later on, we'll just give a brief explanation of DFS.
And talking about the experiment, so we basically so for the project itself, when we were thinking about how we should implement the algorithm, we thought of a little experiment, like a science experiment, I guess you could say, where basically where me and Jason, we're both J&M Consulting Corp, where a hacker approached us and wants to know which algorithm is faster. between breadth first search and depth first search, since depth first search is another similar searching algorithm that is always compared with breadth first search. And then to kind of distinguish the difference between them, well, to kind of define what breadth first search is, and to really figure out why breadth first search is a better option at some scenarios, or I guess at most scenarios, we needed to compare it to depth first search. And in this example, as like one way hackers can abuse algorithm is by applying graph theory and folder organization. And then, so theoretically, the breadth first search is faster, but we wanted to figure out why or how.
Or how
So in
much?
this,
Yeah, by how much? Yeah.
yeah, so in this instance, the hacker is looking for the pictures folder, for the pictures folder. Since folders are stored in a hierarchical fashion, in order to search for the pictures folder, the hacker uses breadth first search to quickly discover the folder and grab whatever information it contains. And then moving on, Jason will
So
describe the design of the breadth first search.
yeah, so it's a simple design. Breadth first search uses a queue. So when you ask a node, do you have a path to V? It will add all of the nodes children into the queue rather than going recursively. So in the picture, you can see just how it starts at S, goes to A, then goes to B, B to C, D, G, H, E, F, I, and K. So it ends at K pretty much. It will pull the first node from the queue to check if it is the final element, and if not, it will add all its children to the end of the queue.
So when we're searching for F, for example, we have a queue already set in place, starting with A, the root A, so that A gets called, it gets sorted into, not sorted, but it gets inputted into the queue. Then it'll ask A, is A what I'm looking for? A is not what I'm looking for. It'll dequeue A and add E and B. Well, I guess it'll add E and B before it'll dequeue it, and then it'll dequeue A. And then it'll ask E, since E is first, it'll ask E if E is F, E is not F, so it's gonna then input the child of it at the end. So the child of E in this example is F, so F is then inputted at the end, and then it's gonna dequeue E and move on to B. Moving on to B, it's gonna ask, is this F? It's not F, so it's gonna input the child to the end, and it'll dequeue B. Now, finally, it's gonna ask F, which is a child of E, is this F? Yes, it is. When it dequeues F, F is the node that it searches for it. So it'll then empty the queue and print out found F, because it doesn't have to continue on, moving on. So it'll just empty the rest of the queue.
Here's a brief explanation of depth first search. So in our technical report and as well in our experiment, we just did a little comparison. Like we said earlier, we wanted to figure out the case given to us by a hacker. We wanted to figure out which algorithm will benefit him more in searching for the folder he's looking for. So for depth first search, we found that the fundamental goal of depth first search is to investigate the graph as deeply as it can. So depth first search looks for edges that branch out from the most recently found vertex B. Only edges leading to undiscovered vertices are investigated. When all of these edges have been investigated, the search returns to an undiscovered neighbor. This operation is repeated by the algorithm until every vertex has been identified. Because this method avoids repeating vertices, each vertex is only investigated once. To keep track of vertices, DFS employs a stacked data structure. This method of searching exhausts the entire tree until it finds the node it seeks, affecting time and complexity. As you'll see later in the presentation, we added our little comparisons.
Yes. And then the design for the depth first search compared with breadth first search. So with breadth first search, to start with breadth first search, you start from the root and then you move to the left, to the right, right, left, right. This is similar to that sorted, what's it called? I just did it today for the exam. It's the heap, similar to a heap,
Yes.
where you start from the root and then move to the left, to the right, left to the right, leftmost node, rightmost node. And then depth first search goes from A, basically it goes A, B, C, and then D, E, F, G, H. So instead of going left to right, it goes down like this, down right here, and down right here. So that's just how the search goes. So you hear A, D, F, C, E, and then A, B, instead of going A, B, C, A, B, C, D.
So for implementation, we found this use visualalgo.net as a drawing board to compare the DFS and BFS. So we actually made our own little graph, and visualalgo lets us run it using breadth first search, and also it lets us run it using depth first search. So what we did, we used visualalgo to draw our own little graph. It has functionalities to let us draw graphs and pick a starting node from the algorithm for the algorithm to start. It even shows you the pseudocode step by step as the algorithm is running.
And then for our implementations for our case, since our goal is to obtain the victim's pictures located in the pictures folder, we created a graph of folder directories to represent our visualization of our project. So these files are actual files on my computer. So I started out with the drive location, which is the root, and then in that drive location, there's 6 different folders. And I put the pictures folder inside of the push bullet, which is an application that I have. Inside the push bullet folder, which also contains uninstall and secret. So this right here is this node specifically is our goal for the breadth first search or the depth first search to search for.
Right. So we then converted the directories diagram to the numbers with 30 representing the pictures folder so that visualalgo.net could recognize and analyze the graph. We ran the graph below twice, one, like I said earlier, one with depth first search and the other with breadth first search. Since the website does not have an endpoint and end node input, we ran a timer on both searches until it reached the picture node 30. We repeated this process for a total of 3 trials and computed the average time in seconds.
And this is another representation of the root folder. So it's the same thing. It's just here we did it ourselves with the root names and everything.
Yeah.
And then that way we can show the same format for our project. But the thing is that we couldn't write words. So we had to do numbers for the actual the input of the website to actually run each algorithm. And our results after running each algorithm. So what we did was we went onto the website, we drew this graph, which is exactly as this graph, and we picked number 30 to be the endpoint. Once we picked number 30 to be the endpoint, we then were, as like a little science experiment, I was clicking the button to run the actual algorithm while Jason had a little timer. And we literally timed it 3 times. So that way, if there is any human error, it'll be minimized as much as possible. And so after our experiment, we came to the conclusion that the hacker is better off using breadth first search. Why? Because breadth first search is 30 times % faster than depth first search. Therefore, the hacker will not get caught using the breadth first search and can execute the malware with no problem. And then below is an average of our results recorded in seconds. So the first trial, we had 46 seconds on depth first search, and then 49.8 seconds on breadth first search. And then moving on to the last trial, we have 45 seconds on depth first search and 29 seconds on breadth first search. It just just doing the trials itself, locating number 30 was so much faster than on breadth first search than depth first search. And the reason is because instead of going through this first folder into this folder, onto this folder, onto this folder, moving back onto this to this, and repeating every single step again, and then going back up and doing it again multiple times, that's what depth first search did. Breadth first search instead looks layer by layer. So it goes to 1, it goes to 2, it goes to 3, to 4, to 5, to 6. And then it moves on to the next layer, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And then finally 20, 21, 29, 18, 19, 30. So it finds 30 a lot faster than going one in through every single first few nodes or four folders.
Correct. So we found that the evaluation, the time complexity of breadth first search, if the entire tree is traversed, is O of V, where V is the number of nodes. If the graph is represented as an adjacency list, here each node maintains a list of all its adjacent edges. Let's assume that there are V numbers of nodes and E number of edges in the graph. For each node, we discover that all its neighbors by traversing its adjacency list just once in a linear time. For a directed graph, the sum of the sizes of the adjacency list of all the nodes is E. So the time complexity in this case is OV plus OE, which is equal to O of V plus E. For an undirected graph, each edge appears twice, once in the adjacency list of either end in the edge. The time complexity for this case will be OV plus O of 2E.
Which is about
which is about OV
which is about the same thing, which vertex plus edges is basically saying height, like how we learned in class. Big O notation of height of the graph.
Correct. So the complexity, we also found the complexity of depth first search, just so we could get small comparisons, because that's what we decided to do for our experiment. So depth first search visits every vertex once and checks every edge in the graph once. Therefore, DFS complexity is also O of V plus E. This assumes that the graph is represented as an adjacency list.
Now you're probably wondering, well, why didn't breadth first search, why didn't depth first search find it as fast as breadth first search when they have the same amount of complexity? Well, which is big O notation of height, big O notation of height here. The reason is because, where is it? Right here. So the reason is because with depth first search, it's only the big O notation of height. With breadth first search, it can be much faster depending on where the node is or the location of the folder. So because over here, the location of the folder happens to be in the middle, it doesn't take the entire big O notation of height to find it with breadth first search, because it's already, it doesn't have to go through 16, doesn't have to go through, well, it already went to that. It doesn't have to go through 16, or it doesn't have to go to 22, 23, 24, and etc., because it doesn't have to touch those layers. Meanwhile, with depth first search, it has to go through the height of the entire tree to then try to find number 30 at the end. And that's the difference between this. Both can go, and both complexities are the same, and both can go up to the big O notation of height. But with breadth first search, it doesn't necessarily have to do that if the location of the folder or location of the node is somewhere closer to the vertex. And for our conclusion, we can conclude that the hacker must use breadth first search in order to not get caught. So since we are J&M Consulting Corporation, when the hacker came up to us to ask which algorithm is faster, so that way they can get access to the pictures folder without getting caught, we decided breadth first search. Now, why? Well, throughout our experiment, we found that breadth first search is faster than depth first search by 35%. And with that being concluded, if the hacker decides to use breadth first search, he has a much better chance of not getting caught when compared with depth first search. As you saw before, it was 26 seconds compared to 45 seconds, which the difference between that about 25 seconds, that could easily been used to like escape or something else instead of still waiting for the program to finish. Jason, do you have anything to say?
No, that'll be all. It was great working on this experiment. It's pretty cool. Finding the differences in like I before going into this, I thought you could even ask Mike. I was like, there's no way that there's such a drastic time difference. And while we were doing the trials, I was just sitting with the stopwatch. I'm like, hey, it's not gonna be much of a difference. But then we realized it's like, oh wow, it's like quite a drastic difference in both algorithms. I was like, oh, that's cool. So
Yeah, and that was only because of the location of the folder. If I included the folder either deeper in the graph, as in further away from the vertex, then the deeper it goes, then that's when depth first search it will be more.
Yeah.
And also it depends where, if it was on the leftmost side of the left subtree or the right subtree. So that's why breadth first search is always the ideal option, because not every computer in this scenario, not every computer has the same amount of folders and the same amount of subfolders to get into the pictures folder. So if I hack another computer that's not mine, like Jason's, for example, his pictures folder could be right on the desktop. Boom, I found it in a second, in the first layer, instead of going through each of his folders, instead of going to his application folder, which is what happens to be first because it's located, it's organized with an A. Instead of having gone through all his applications folder, I just go application, bingo night, and then pictures. Boom, I found it right away. So that's why we used and we suggest breadth first search for the hacker to complete his malware attack. Thank you very much for listening.
Thank you.